We'll start with the definition of a topology. It seems like a good place to start. So a topology on a set X is a collection T of subsets of sets of X having the properties first thing we need is that the empty set and the set X itself are in the topology. We need to have the union of the elements of any subcollection. Any subcollection of T is in T. And the intersection of the elements of any finite subcollection of T is in T. So topology is a collection of subsets. We give the empty set itself, all arbitrary unions of elements, all finite intersections of elements. And so then we say that a set X for which a topology T has been defined or specified is called a topological space. Topological space. And they denote it's kind of like with groups. Instead of always saying G star, you just say G. It's implied to be in a group. They had like an ordered pair, so it's an ordered pair of your set with the topology, but then if you just give it that X with the topology. So then open set is a pretty big deal across these three sections. Just a little important. So X, T, be a topological space, a subset U subset X is an open set of X if U belongs to T. And then there will be different this is the general way they start with open sets, but then more specifically, we'll define open sets in terms of we return to open sets, not in this one, but in the next section. Okay, so I'll do an example, I guess, on the bottom here. The different you can define lots of different topologies on the set that contains three distinct elements, say A, B, C. So now what's interesting is in this example, there's a correlator or there's a definition of some other stuff that made sense after I did this. But if we say we have A, B, and C, so if we only take the topology, which is the minimum requirement, so empty set and then the set itself.
Yeah.
So, and it's a trivial topology. But we could also do something like, so if I have A, B, C, I could take, well, I always have to have this one. But I could take the subset of A and B, I could also have a subset in that collection B and C, but if I do that, all of the unions have to be in there as well. And all the finite intersections, so AB with BC gives, I need to have then the subset with just the element B is in that. In order to make this a topology, otherwise it's not. So this would be the topology T, where we take the empty set with X, and then we also have A, B, we have B, and AC.
BC.
Oh wait, yeah. And then you don't always have to have the overlapping, so that I also found an example for union, or rather an example of you can't just take, because when I first read it, I thought it was a little loose, but these conditions are really helpful.
Yeah.
So it's like if I take like A and then I take C, just because I take any collection of the subsets doesn't necessarily mean this is a topology. Because here, this is violating if I don't have A union C in here, so I would need to make it a topology, I would need to add
Right.
AC like this.
Mhm.
So that would be a topology, but without it, it's not a topology. Okay, so then from here, this motivates definition of discrete topology and trivial topology.
So they don't define closed yet?
No, they do close in the section on basis.
Oh, okay.
Yeah, I think that's more of just an editorial thing.
Mhm.
I don't think it was necessarily like they had to do it that way.
Right.
But so the discrete topology on X is the collection T. It's the collection T of all subsets. All subsets of X. And the indiscrete topology, which they're also going to call just the trivial topology, on X is the collection that's always given by empty set.
Mhm.
Discrete. So in this set, a discrete would be I would take A, B, C, and then all of these. So then I would need A, B, and B, C, and then I would also need A with only C. So
Mhm.
however that could be drawn,
Yeah.
etc. So then that's all of the possible subsets using those three elements, and then that's discrete. I think, and then that was originally what I was conflating with topology. I was like, why can't you just take them all? And I didn't realize that you don't have to take them all. You just have to have the right ones again. So then we can define the finite. So then there's a few different topologies that he goes over. What is this?
So in some regards, the discrete is the maximal
Yeah.
and the trivial is the minimal.
Yep. So if we have let X be a set. Actually, no, if I erase this, I can do the proof of this underneath. This is a proof that I had fun doing, just because it was, I hadn't done much rigorous set theory before in algebra, so it was kind of a good exercise to do. So let X be a set and TF be the collection of all subsets, collection of all subsets U of X such that x minus u is either finite or all of x, then TF is a topology on X. And we call this called finite complement topology. So we can show that this is actually it satisfies the definition. So the first thing we can do is we need the empty and x to be in there. So if we were to take the subset x minus x is finite. So that means that x is in our collection, and also x minus empty is just x itself. So we get that the empty set is in our collection. So that's taken care of. And so what we're going to do is we're going to let U alpha be an indexed family of non-empty subsets, or we can say elements of the collection. And if we do this, then we can basically, we see that if I need this, so if I'm subtracting this subset, then it needs to be an element. So x without this union of the U alphas is if you have your collection. You take the union of all the collection elements. And so that's going to form a larger set. It's going to be at least bigger than, if not equal to. But if I were to take individually the set without each individual piece, then at the end result, if I take all the separate pieces, what I'm really interested in is just at the intersection of the separate pieces. That would be the same equivalent of me taking away the union of the whole. So I have this is really just the intersection of each individual set being subtracted from X.
Yeah, that's cool.
But what's nice is that we know that this intersection, because X minus U alpha is finite. So the intersection X minus U alpha is finite, because when we proved intersections of finite sets are finite in the previous, I think that's 2 weeks ago. And so we can have that X, or at least the unions, arbitrary unions, will be in our topology. So now we just need to show intersections are going to finite intersections.
So, all right, unless all of them are equal to x, right? If
So like all of the sets in here.
all of this, like all the UAs are the empty set, maybe.
Oh, okay. Well then, but then you just revert to that case.
Right.
So then we're gonna have
Right. So assume that there's right. So you assume that there'd be one that isn't empty. Then right.
Yeah.
Then we go. Yeah.
do it a little differently for the intersections because we know it has to be finite, so we restrict it to U1 to some UN. And these are non-empty elements of TF. So again, we see that if I'm going to take the intersection, a finite intersection, so 1 to n of my UI, then again, if I'm taking, I intersect all of these in this collection, that's the result that I subtract away. So what I'm really doing is I'm taking every single one of these in the collection, I'm subtracting it away from the original set, but then I want the sum total of all of those in it. So I'm going to take the union of each individual difference of the set away from the X, or the subset away from X. So I get a union, I equals 1 to n of the taking each individual subset away from the total. And then again, we do this to invoke work that we've already done. We have a finite union of finite sets. And so that's finite, and we have that the intersection, arbitrary intersections, well, not arbitrary, sorry, finite intersections will be in the topology. So then all of this is, we get that X with TF is a topological space.
Nice. I think there might be a little, I mean, it's correct, but they'd probably tidy, like, they'd be a little careful more on the going from the trivial cases that you did first to the more general case. They'll probably would have some words. Assume.
Oh, yeah.
But apart from that, it's great.
Yeah, because sometimes it's easy to lose the assumption under TF being that we're assuming this to be we're assuming this condition to be true.
Right.
Yeah. But that's words.
Yeah.
It's already enough writing words and definitions down. It was really interesting. I was doing some Greek exegesis, and this is grammar rule or syntax rule, and I read it and I thought to myself, linguists could really use just what could be said in 8 pages really could be a definition.
Right.
And since linguistics is actually kind of difficult, it's not outside the realm. Like, they should just add chapter 1 should just be the basic set, like not even complicated set theory, just the language to do it. Because you could define so many things so much more efficiently. But
that's your next project.
Yeah, no, I submitted that as my homework for my Greek conference. Like, hey, you could do it this way. It's much easier. Okay.
Now Jeff Lamb.
Yep.
He did undergraduate math, so he could appreciate it. Maybe.
Yeah. Or he would just think I'm doing too much, which is true. I am. Okay. Let's see. Oh, this is a good definition. Yeah, it's talking about finer and coarser, etc. So suppose that T prime are 2 topologies on set X. So if we have that T prime contains T, basically it has more subsets. We say that T prime is finer than T. And if T prime is strictly containing T, so they could be the same. Strictly contains, and we say that T prime is strictly finer than T. And so on the other way, we define T the T prime as coarser and strictly coarser, respectively. Because like the construction of the definitions are analogous, it's just you could say the other way if you wanted to. Okay. And then comparable is going to be we say that T is comparable with T prime, if either of those two things, that could be the case. We could have that T prime is finer than T, or we could have that T is finer than T prime. Either way, just a way to relate them. Which when we were doing the example with like the A, B, and the C, they don't necessarily have to have the same subsets, and if they're not related to each other, then there's no relationship of containing the other one.
No comparison.
Okay, basis. What time is it?
It is 4 minutes to 11.
Okay. That's tough. Since thankfully order topology is pretty much just defining arrays, then I think we'll be fine. This is important though. More important if we had to, I just push order topology to next time. Okay, so if X is a set, a basis for a topology on X is a collection B of subsets of X called the basis element, called the basis elements, such that, and then we have two things going on here. First thing is that for all of the X in the set, there's going to exist at least, there could be multiple,
Right.
but at least one basis element B containing X. Which makes sense. I mean, we account for all of the X in the set with the basis, and then also if we have that, we have X is in one of the basis elements, or rather, if we have two basis elements and then it's found in the intersection of two basis elements, then that's going to give the existence of a basis element that also has the X such that this basis element is a subset of that intersection. And so that's kind of neat because sometimes and a lot of times this is actually just, it's a subset of, it's an improper subset, or that intersection is in itself just the B3 is the intersection, but this could contain other things. So this would be like a finer subset, including the elements instead of, where these could be larger basis elements.
That's interesting.
Okay, so those are the two properties for basis elements and basis. So if B satisfies these properties, we define the topology T generated by B as follows. So first thing we do is a subset U X is said to be open. So here's where we return to open in X. If for all of the elements inside of our subset, there will exist a basis element such that X is contained inside of the basis element, and that basis element itself is a subset of the subset that is found in. So it's kind of similar structure logically to this second property, but now it's just for an open set in your topology. And then we note that pretty much that it's given definitionally that each basis element is in T. So your basis elements are in the topology because they're subsets of your set. But then this is a more specific one, is that I take a specific subset, it will be open, in other words, it'll be part of my topology. If the elements and every single element that's in that particular subset in the collection, as I can find one of the basis elements, it's going to contain it, so that the basis is contained inside of that subset. So it's not just any basis element, because sometimes there can be multiple basis elements given by the second property that will overlap, but might include elements outside of U. So this is a stronger property because it will give that it won't just be a basis element, but then that basis element itself will be inside of the subset that we chose.
Yeah.
In the topology. Okay. So then an example of this is that if X is any set, then the collection of all 1-point subsets of X is a basis for the discrete topology. Discrete topology on X. And that's as soon as I read this, that's kind of how I intuited understanding the concept. Because then if now the basis, because from linear algebra, you think basis is like the minimum number of vectors to get the whole span. In this sense, this is non-unique bases because then you can choose different kinds of subsets to still have a topology.
Yeah, it's still
but
different.
yeah, but for the discrete idea,
That's
so
the way I usually think about it too. That's where I jump to.
right, because mentally you're just like, okay, so then I can take, if you're gonna have a set of elements, then just make every single one of the elements individually a basis element, because then all of the finite intersections and all the unions are gonna be in there. Yeah. Okie doke. So let's see. Let's get to this was. Trying to see what, so it's. Here's what we do. This proof was really, really fun to do. So, but it'll take a little while. So I might not get to order topology. But I wrestled with this for a while because it was confusing. So this is gonna basically talk about this is showing, I'm going through and showing as exercise that the whole thing with the discrete topology. So if you take each of the individual elements in the subsets. So if we have U being the empty set, then it's true vacuously. So vacuously satisfies. Man, I need to learn how to write again. Vacuously satisfies openness. Okay, so then for all X in our set, there's going to exist a basis element with X inside of that basis element. So that tells us that X is in itself in the topology. So we're verifying that both the empty set and the set X are in the topology. So now what we're going to do is we're going to index U alpha over J. And this will be indexed family of elements. Next family of elements of T. And so we want to show, so if I take U, one of these subsets being this union of the alpha and J of the U alpha, this is in T. So if we gotta show arbitrary unions is in the topology. And so what we do is we say, okay, if I have some element in the union, in U, then this means that there has to exist one of these alphas in J, such that X is found specifically in U alpha, right? So if I'm gonna say, okay, let's have an element in here, one of these, if we're pulling it from the union, is going to be in there. And then we have from if this is a topology, U alpha is open. And if U alpha is open, then by that definition, we're given the existence of a basis element then, such that X is going to be found in that basis element. And on top of that, we get that basis element has to be definitionally a subset of U alpha. And if that's true, then our X that is in the basis element. Wait, I'm writing the same step today. We have X in B a subset of U, because U alpha is in this union, so this is in itself a subset of the union of all of the individual sets. And this is the property from which we can give that U is open. Okay. And then the intersections is far more confusing. So what we want to show is that U1 and U2, if we have these, we're going to basically induct it to be true for all of the finite intersections by just starting with this case. Oh, I did the proof of the Cartesian, so like finite products will always, yeah, okay, so it's a similar strategy actually. U1, U2 in T, and this tells me, and we want to give that in the event that you have two of these subsets, that their intersection is in T, right? So it's like an example of what we're trying to generally go with all of the intersections, or all of the finite intersections. So what we're going to do is we're going to start with X being inside of this intersection. And because of this, we can choose, so we're going to choose an element in the basis, a basis element B1, where X is in B1, and this is, I'll just state the property, and that's going to be in there. But also, because we have an intersection and X is not finds in between these two, that means it's in both of them. So we can also choose a second basis element B2, where X is in B2, which then is a subset of this other subset in the, or I should call it an element, I guess, to make it less confusing.
I see. So that's why we needed that when you did the definition, the B3 is in the
exactly. So it's pretty cool. So then we choose read my notes from the definition of basis, what it means to be that basis element, that second property comes in. And then we're given the existence of this third basis element where X is in that. And we're given that this has to be an improper subset of B1 and intersects B2.
Perfect.
Yeah, so that's pretty cool. And then we have that X in this third basis element, which we know to be in the intersection of U1 and U2, gives that U1 intersecting U2 is in our topology by being open. So that's the first case. We get that if we have just two, then that's going to be, and so visually, so if I had like, here's U1, one of the subsets in the topology, and here's another subset in the topology. And so here's the intersection. So we're saying, okay, we can choose an X that's in U1 intersects U2. But because by definition, I can have, at least in contained in U1, not necessarily restricted to the intersection, but I could have some basis element that's a subset of U1 that still X's could be a part of, but it could include things that are not necessarily in U2. And at the same time, there could be something arbitrarily true over here as well. And so that's why we need to invoke. It's not sufficient to just have the other two, because you're not guaranteed that you're restricted to just here. And then we invoke that, okay, we have B1, B2 intersecting as basis elements, giving our third basis element that'll have our X.
Yeah.
Okay. I don't know why that took me so long to figure out.
So that's good.
But it's tricky. The induction step is not bad after this.
Because when you wrote it down originally in the definition, I thought, what? We need it. It's right there.
Yeah. It happens to be convenient when we need it. So then, now we want to show through induction. Munkres would put that induction in quotes just to be cheeky.
Right.
That the U1 intersects to UN is in T. So this is trivial for it. And is equal to 1. And I reserve trivial for only the things that I personally as an undergrad think are trivial. If you just have the set, yeah, it's an open set in your topology. So that's pretty good. Not as confusing as some of the other things he's called trivial. Now, if I take, again, we're going to split up these, especially if it's finite. The trick is just take n minus 1, and then you get 2 sets, because we've already proven that it works with 2 sets. So if I do the intersection UN minus 1, and then intersect this set with UN, then that's pretty much it, because then this right here is open by the induction hypothesis. And then on top of that, we would just say, okay, this is a set, and so we would we have a intersection of 2 open sets, as proven before, is open. So then the finite intersection will be in our topology. So that's how we can prove that the basically that easy basis. If we just take all the individual elements, that'll give the discrete topology.
Yeah, that's nice, because we explicitly see why that line in the definition is needed.
Yeah.
I like it.
Okay. Good stuff. It's definitely, I'd say that the challenge of this has been, it's so up there in the clouds that it can take a second for the fog to condense on the glass, you know? Okay, let's see, I'm basically just saying that if you have a basis on X, then your topology would just be the collection of your unions of your basis elements, which is the same motivation for why it seems intuitively, we just intuit, okay, just take all the individual elements as subsets. Because then you're not making it, like, you won't leave something out on accident if you take unions and intersections. Or rather, if you have disjoint. And I was thinking about it because I looked ahead for research. So if you have like a cover where you have disjoint sets or partitions, then if they don't have shared elements, all of your subsets all the subsets that would be finite intersections are given to be empty.
Right.
And so then you clear that issue. Okay. That's just the same thing that I said. You can express open sets as unions of your basis elements, which is basically, he's distinguishing from linear algebra, where when you have a basis, that will be a unique basis for your vector space. But with these, that discrete topology is not the only basis you could have to cover a topology on X. And then, okay, no, this isn't good. I'll put this in the lemma, and then I think we can actually hit the order topology. So
Yeah.
Yeah, so if I have. That's an element, I need the collection. Okay, so two collections, two bases, B prime, B bases for the topologies T prime respectively on X. Then the following are equivalent. Are equivalent. So if we have that T prime is finer than T, that's true if and only if for all of the elements that are in your set and B in B containing your element that you chose, you can find a basis element in B prime such that X is also in B prime, which then itself is that proper subset idea of the other basis element. So finer, you had a good analogy. So it's like if you have, stones, and then you can break apart stones and it turns into smaller rocks. So it's the idea of, okay, this has more subsets and they're comparable. So this T prime has all of the subsets that T has, and then also more. And so if you can find a basis element for every single, and you can find the basis element for all the elements in X in B less precise, basically, then you just find the analogous one. Sometimes it'll just be the same thing, but in the event that it's finer, you might actually have one that's a smaller subset, fewer elements that contains the same element. That's a good reminder of that definition. Okay, so standard topology on the reals, that's kind of important, I would imagine. And this is where he starts to talk about open and closed stuff. If B is the collection of all open intervals in the real line, and it was cool to see why we call it an open interval in the topological perspective. So if I take this interval AB, which is on an over an ordered set, then the topology generated by B is called the standard topology. Standard topology on the real line. And then whenever we're considering the reals, then this is the default assumption, assumed topology, unless we're specifically specifying something else. A lower limit topology is going to be a collection, so I won't repeat all of the words, but essentially if we want the lower limit topology on R, limit topology on R, it'll essentially be a collection of all of the intervals closed on the bottom A to B, X, and then A less than equal to B. That'll be a lower limit. He didn't define an upper limit topology, probably because either A, he thought that was a waste of time, or you could just intuit that if you wanted to. The K topology is if you've got elements. I might be able to fit it on the bottom here. So K is going to denote the set of numbers of the form 1/n, where n is a positive, like that. So all of the open intervals AB of the form, we take AB without K. Then this is going to be what we call the K topology. G denoted. So apparently this is important for later. I don't know why yet.
Heard of it. I'm not sure I understand the purpose right now.
Oh, the denotation for the lower limit one is R sub L.
Okay.
R sub L, by looking, R sub L and R sub K are gonna be finer than just the standard topology on R. But these are not comparable topologies.
Oh.
Well, because if you're taking out all of your the positive rationals 1/n, then you're gonna be missing, so the subsets will be different because you've taken out those specific elements from the lower limit topology, which will include all of the 1/n's. Okay. Let's see it. We have hit open intervals, close intervals, half open intervals, and the raised. Because we talked about this in analysis.
Mhm.
We don't call it topology because it's just implied.
But we use the words.
Yeah.
Or the words.
Right. So we're defining basically X together with an order relation, simple order relation. And then there are 4 subsets. So when we talk about an interval, I'll just do it like this. There are 4 intervals. There's an open interval in X, A, B, X, A less than X less than B. There's a closed interval. And I can't remember what we discussed last year about the half open ones, but A, B, X, A less than X less than B. Did we call them half open?
Mm-hmm.
Yeah, I think that it sounded familiar. And there are 2 half open intervals in X. And that's going to be A, B, and closed A, open B. All the familiar stuff. Open intervals in X is a nod to the open sets when a topology is put on X. So I didn't know that's why we called it open.
Mm-hmm.
And then the order topology is basically going to contain your basis. The basis is formed by taking all of the open intervals in your ordered set. Then you're going to take all of the half open intervals, where the bottom is the smallest element if it exists, true. And then if you have a maximal element, then you take all the half open intervals where that's the maximal element, and then you go the other direction. So if you take the collection of all of those, we call that, you generate a topology, which then is called the order topology. So the standard topology, that's the whole reason why we did this section. So the standard topology on R is the order topology. So just to clarify something, if there is no largest element, and if there is no smallest, then you defer to the open. Yeah. So standard topology in R is the order topology derived from the usual order on R. So then they're expressing the standard topology in yet another way.
Yeah.
And then the rays, we have an if we're given X together with a simple ordering, and we have an element A in our set, then there's going to be rays. So the open rays. And I remember learning about ray, like random thing in middle school. Where it's you can take A to, you know, infinity or whatever that means for your ordering. So whatever is greater than your element. And then also the other direction, whatever's underneath or less than. And then the closed rays. Or what it sounds like, you just fill in the dot on the real line, or if this is an abstract ordering, it still works as long as you include the element A. So that's kind of what's cool, is it's given a language for taking ordering outside of the reals so that we're no longer restricted to only doing examples on the reals for topology, which kind of is the whole point, I guess, of abstracting that kind of stuff. I still have no idea what I think about how people choose to apply this kind of thing. But I guess we'll find it, because I think I'll be doing the product topology either next week or the week after. So there'll be some other things. It's definitely point set. All of the part one is point set, and
Right.
algebraic will be next semester.
Yeah. So that's pretty much standard. The only thing